look at 3 and 4 for 19. Like I said, there's no labs for these. They are what they are. We're going to look at some more dealing with entropy and the third law of thermodynamics, and then we're going to look at standard molar entropies, which are really easy to figure out. We've actually done them before with enthalpies. Okay. So first things first, we're looking at molecular motions and energy. We're looking at how molecules interpret entropy. So we talked about yesterday with entropy being the amount of randomness or disorder that something has. The more disorder, the higher the entropy. So we're going to look at how molecules store energy. There are 3 kinds of motion for molecules and how they store energy. You have translational, which means that the entire molecule moves. You have vibrational, which means that just the atoms move toward and away from one another. And you have rotational, which means the atoms spinning like a top would spin. Okay, so you can have the entire molecule moving. So a water molecule moving from one spot to another. I can have just the H and O vibrating in place in a water, and I can have the entire molecule rotating or spinning around in a circle. Those are the 3 ways that a molecule can store energy, and 3 ways that they move. All right, you can make qualitative predictions about delta S or about S. Okay, an increase in entropy parallels an increase in temperature, volume, and the number of particles that move. All right, for example, if you vaporize water, okay, meaning I go from my liquid to a gas with water, your molecules are becoming more spread out, which means what they have what we call more degrees of freedom, meaning more ways that they can possibly move. Okay, if you ever hear later on when I talk about degrees of freedom, that just means, or freedom of motion, that means they can move more. They have more ways they can move. They can vibrate, they can rotate, they can move. Okay, in a reaction, if you decrease the number of molecules, if you decrease the degrees of freedom, that means that you're going to have less entropy. So just overall for a reaction, very basically, okay, if you have less stuff, if you have things that are bonded together more, you're going to have less entropy just because they have what we call, again, less degrees of freedom, or they can move less. Okay, entropy will increase for if I go from a solid to a liquid. It increases if I go from a liquid to a gas. It decreases if you go the other way. Okay, and if I make any kind of solution, that also increases your entropy as well. So if you increase your number of molecules, if you make things into a solution from a solid, if you make anything that gets the particles further apart, that makes a higher entropy. You have more disorder. I have more options for things to be more random. If you add more reactants, I have more entropy. I was thinking of it kind of like one of those like ball pits at like McDonald's or something like Chuck E. Cheese or something. Those have all kinds of colors. That's a huge amount of entropy. If you took all the red ones out or all of the blue ones out, it would have less entropy because you'd have less colorful possibilities for randomness. All right, now we're going to predict whether delta S, my entropy, is positive or negative for each of the following. You're going to assume that they occur at constant temperature. Help yourself out a little bit there. I'll look at A. A goes from water as a liquid to water as a gas, so that is going to increase my entropy, which means it's going to be positive. You're going from a liquid to a gas. I am more disordered. If I go from 2 things in a solution to something being in a solid, the particles are closer together. They're forcing them to bond together, which means that it's going to be negative. You're becoming more ordered. If we look at C, I have a solid and a gas combining to make a solid. I'm also going from 7 particles to 2 particles, so things are becoming more ordered. I have more things put together, so that's negative again. And the last one, I have both of them are gases on both sides, and I have 2 gases on the left and 2 moles of gas on the right. So technically here, we're going to be pretty close to 0. It's like about, okay? It'd be about 0 or equal. Third law of thermodynamics. If you decrease the energy of a system, meaning you're lowering the temperature, that means my particles are going to get less and less active, So the energy that is stored in your degrees of freedom is less and less, meaning my entropy gets less and less. All right, tying into what we call a third law of thermodynamics then, is that at the point where your temperature is absolute zero for any pure crystal solid, there is no thermal motion. If you get absolute zero for a pure crystal solid, you should technically have absolutely no motion. That's your third law of thermodynamics. Now, no one actually gets to absolute zero. You get into the, like, I think the closest somebody got was to like the billionth place. Now, as soon as your temperature increases, your entropy will increase because your particles gain more energy, which is all this is doing. I go from a solid to a liquid to a gas. I get more temperature, I get a higher and higher and higher amount of entropy. Okay? You will see these like abrupt changes that happen when your bonds are broken and your molecules are now free to move. Like if I go from a solid to a liquid, I store up all this energy, then they break, and all of a sudden, now I can translationally move when I'm a liquid, meaning move around my entire container. I add more and more temperature, get more and more entropy. Now I kind of store all this temperature, and then they break. Now they can actually rotate a lot more because they're gas, so they can rotate and move. So the reason that this right here is bigger than this one is because it takes, or I get such a higher entropy out when I have a gas than when I have a liquid. Because you're adding that like third degree of freedom that my liquid does not have. Alright, section 4, we'll look at entropy changes in chemical reactions. And yours should say standard molar entropies.
Yes, standard molar entropies.
Okay, unfortunately, for standard molar enthalpies, meaning, entropy, thank you. I'll do that a lot. Meaning, that's your entropy for something and a mole of it at some standard that we set. Okay, so that's kind of what we're getting at here. These are going to be molar, meaning a mole, entropy at set standards. So we talk about a standard molar entropy. That's what that means. If it's in a standard state, that means a set temperature. Normally, we're looking at 298 Kelvin and 1 atmosphere. Usually. They'll usually specify up here in the top, and they'll say, okay, that's like at this particular temperature, and it'll also sometimes say 1 atmosphere.
Why did they choose 298 Kelvin?
That tends to be room temperature. 273 plus about 25. Unfortunately, for these lovely delta S values, there is no existing way to measure these values. We don't have calorimetry, so there's really no real method to measuring.
They just guess.
They base them off of other things. Okay? What they do is they experimentally you can determine at absolute zero the value for your entropy for many substances. So based on a reference point, they figure out what everything else should be at that point. So they kind of make their own reference and then put everything else off of that. There's no calorimetry here. Entropies are always in a mole, like I said. Okay? Some notes about these S values. Unlike the entropies of formation, these molar entropies at room temperature for things are not zero. So remember way back a long time ago, we talked about delta H values for like H2, O2, things like that are zero. Not so. For entropies, they have values because they have some amount of disorder to them inherently because they're not at 0 degrees Celsius. So these values are all in the back of your book. They're that last column that we haven't talked about yet in appendix, I believe, D, C or D, one or the other. Those big chart with the delta S, delta H, that kind of stuff. These are not zero at, how should I say, at room temperature.
If you will. Thanks for teaching that, David.
What you'll also notice is that molar enthalpy quality or quantities for liquids and liquids and gases should be more than solids. Solids should be the lowest because they have the least amount of disorder. Liquids and gases have more disorder, so their delta S values or their S naught values are a lot more. If you notice, I have like a little knot. That's what those are called. Zero, they're called knots. Okay, that means at standard. If you see a delta, that means a change. So if you see like that means at a standard. Molar enthalpies, or entropies, sorry, entropies increase with increasing mass, meaning like molar mass. The heavier they get, the more entropy they have. More atoms you have, the more my molar entropy is. Because I have more atoms, I have more degrees of freedom. So something like CH3OH is going to have more molar entropy than something like sodium. We've done this before, and it should look familiar. Just with enthalpies instead of entropies. If you see a delta S is equal to, like for a reaction.
S product.
If you want the delta S, I should have a little knot there actually. For a reaction,
What are the N and M?
you need the N and the M, which are the coefficients in your reaction, or in front of that particular compound. And it's always products minus reactant. This is on your green sheet. It should be like, sometimes it's right underneath the H one. So if you want the overall standard entropy of formation for a reaction, you take the products minus the reactants. Alright, let's try it here. It's pretty easy. Delta S for the synthesis of ammonia from N2 and H2. And at 298 Kelvin, they give you the reaction, which you should have had a long time ago. Okay, products minus reactants. So I'm going to take 2 times whatever the delta S for NH3 is, minus the sum of whatever N2 is, and there's 1, so just 1, plus 3 times whatever H2 is. And I'm looking for these S values that are in the back of your book, and they'll be in that appendix. Okay? Just be very careful when you look these up. They're looking in the right column. That's the hardest part to these. I'll look in the back and it'll tell me that this is 192.5 minus N2 is 191.5 plus 3 times 130.6. And I'll get negative 198.3. And these are usually joules per mole Kelvin. Should be like one more little bit and then we're done. Values above that we looked at are values for standard entropy changes for our system. But what about your surroundings? Okay, you want to think of a surroundings as a large constant temperature heat source. So you want to think of the surroundings as a large constant temperature heat source. Okay, the change in entropy of your surroundings depends on how much heat is absorbed or given off by my system. So whatever my system gives off is going to change what my surroundings kind of absorb or lose, depending on what your system is doing. And we can figure out how much my surroundings will absorb if my system releases it, based on the actual enthalpy change for a system.